Okay, I suggest we slowly start, and we have today a new iteration of AI seminar, and we are happy to have today Quentin Berthet, who is currently a research scientist in Google DeepMind, but previously he has well, he held various positions in the University of Cambridge, in Caltech, in Princeton, and so on. And the topic of Quentin's talk today is perturbed optimizers for machine learning. And I think that's a very interesting topic, which will be very interesting for our audience. And it's actually very important for applications, I guess. So Quentin, please go ahead. The floor is yours.
Thank you very much, Maxime. Thanks for the invitation and the very nice introduction. So today I'm going to talk about, as Maxime said, perturbed optimizers for machine learning. So this is a presentation of a line of work that we've had over the last few years with some of my colleagues at Google. And the aim is really to include as many operations as possible in end-to-end differentiable systems. Okay, so the first work that this is based on was from a few years ago with some of my colleagues at Google and Francis Peck at INRIA. The idea is that in a lot of machine learning these days, at least in a supervised setting, what you have are input responses in a data set, and you have a parametric model. So as an example, a neural network with weights, GW. And the goal is to have the GW of xi to be close to yi at least on your data set, hoping that this will generalize well. And often how this is done by minimizing a loss between these predictions and the ground truth. So, as an example, in classification, you have images and the ground truths are one-hot vectors, labels. And the workhorse of these optimization methods is using gradients of the loss that in a lot of settings these days now are computed automatically with automatic differentiation or backpropagation. So now this is all fine in practice. The problem is, what if these models contain non-differentiable operations? So here, non-differentiable has an asterisk. The idea is that you care about operations that might sometimes have zero gradients or for which the gradient might be complicated to compute. How do you handle that? And at first it seems a bit counterintuitive because you're thinking of these weird functions that look like Brownian motions that jiggle a lot, right? These non-differentiable functions. You think this is not something that comes up naturally in a machine learning pipeline, but actually there's lots of natural examples of these. So essentially any discrete decision in machine learning is in this setting, and there's full of them. I mean, a lot of computer science is based on discrete math and a lot of these discrete algorithms with outputs that are not naturally differentiable. So if you want to, as an example, rank elements, right? So if you have k elements and their features, and the output of your model is scores for these k elements, and you want to rank them, so you want to compare them to 1, 2, 3, 4, 5. If you try to make that by saying essentially I'm going to rank my elements, I'm going to predict some rankings, and then try to get a loss that makes sure that these rankings, y star or theta, are close to y. This is not something for which there's an easy gradient. Most of the time it would be 0. There's plenty of other examples like this. So you can have shortest path between 2 points based on edge costs, or you can have, in the case of classification, you can have classification scores for each class and a y star that's a one-hot vector, right? So if you take the largest element, if you just have a 1 somewhere, the largest element of these logits, and you compare this to a vector of one hot, then this seems like a challenging task to tackle. But actually, what you all know is that there's a very nice workaround There's a very nice workaround in the case of classification, where you would say that you would not take the argmax here for y star of theta, where you would take a softmax, and so this corresponds to taking a cross entropy loss between the y's and the thetas, and this softmax, right, this proxy of the max for classification is something that we would like to generalize to make happen for any sort of discrete decision. So the idea is that we would like to see this whole system be end-to-end differentiable. In general, for these with these discrete decision operators, they are not. But if you can just change them slightly, so one of the examples is the softmax, then suddenly they can become end-to-end differentiable, which is really what we want. So how does that work in practice? So all of discrete decisions can be written as optimizers of linear programs over some polytope, convex hull of a set in RD, right? So as an example, you have, if you're taking the maximum element, this will be the linear program over the simplex, right? So convex hull of one hot vectors. But you could also take more complicated polytopes that will have all of the possible rankings at the extreme points, or all of the possible shortest paths, or things like this. And now you can consider two things. You can consider first the value of this linear program f, and y star, so the solution of this linear program, the argmax of the linear program, which happens to be the gradient of this maximum function. Right, so this is a very nice operation, but in practice, and you can see this already on this drawing, right? If theta moves around a little bit, then the issue is that y star is either not going to move at all, or it will suddenly jump to a neighboring point, to neighboring extreme point. So the gradient is piecewise constant. It's 0 almost everywhere, and then the function is piecewise constant. It's 0 almost everywhere, and then suddenly it's discontinuous. So it doesn't have a well-informative gradient defined everywhere, and this is one of the things that we would like to change. So the way in which we address that is by introducing stochastic smoothing, right? So these random perturbations. The idea is that you have this vector of costs theta, and you add some stochastic noise, right? So small epsilon z perturbations to it. And now instead of having, the solution of this problem being y star of theta here with probability 1, having all the mass here, you have a bit of mass in all of the other points, right? You can see here as an example, for this particular z, the solution would be here. For other z, it would be in other places. And now what you can do is you can average all of these, and you get something here in the interior of the convex hull, right? You get y epsilon star of theta, right? So it's the expectation of the argmax, and it's the gradient of the soft value of the perturbed value of the maximizer. And now this operation, one thing that I claim is that it has a bunch of really nice properties, in particular in terms of differentiability. Okay, so now why is this a nice model to begin with? Well, it's not, it's something that's been around for a while. This sort of model of optimal decision under uncertainty was introduced by economists in the 50s and 70s. The idea is that they wanted to reconcile this sort of apparent paradox between the fact that there's this assumption in economics that people make rational decisions, optimal decisions, right? Optimizing their utility functions, and the fact that people don't all make the same decisions, right? So one of the things that they said is maybe people have uncertain or random knowledge of their utility, and maybe this is why there's some uncertainty. They're all taking slightly random and different decisions. Now this means that it creates a very nice model. It creates a distribution that's parameterized by this continuous parameter p theta over a discrete set, and it has this expectation y star of theta that's one of the objects that we care about, this perturbed optimizer. So you can care about the whole model, you can care about p theta, or you can just care about y epsilon star of theta. And this is related to these questions of, perturb and map that were introduced by Papandreou and Newell, and follow the perturb leader in online learning, where it's used to promote exploration. So here, as an example of this, you can see in the picture, if you have a situation where you have some images. So these are the features, the pixels, right? So this is taken from an old video game. These features they correspond to some costs, so some hidden theta of travel costs in this graph. And now, if you want to take the shortest path from the top left to the bottom right corner, one of the solutions in the middle here is given in yellow, and you can look for the same solutions, but by introducing a bit of noise, right? So you can see if you introduce a little bit of noise epsilon, but epsilon is 0.5, then this explores a little bit, the areas, north or south of this lake and stone. And if you add epsilon that's 2, it adds even more perturbation and it explores even more, right? So these are the objects that we get here. These are the soft solutions compared to these hard solutions. There's one example that helps a lot to visualize what's going on, which is over the unit simplex. So in dimension D, if you add Gumbel noise, so in this case, before adding Gumbel noise, the value of f is just the maximum of the theta I. And once you add some noise, so you can write this out explicitly, the solutions that you get that the soft value function, the perturb value function, is the log sum exp. The probability model is the Gibbs distribution, right? So it's proportional to this scalar product divided by this temperature epsilon. And the perturbed optimizer here is the softmax, right? So exponential weights over the theta I, right? So this is one example to have in mind, and that you can see as well kind of connects well what the softmax that we all know and love, and it's sort of perturbed analogs for all these other problems. And this shows that our setting, or perturb setting, is a generalization of the softmax. Now, this is one example where you can very easily write everything explicitly, but in general, you cannot. In general, if you try to explicitly write out over all possible paths from this pixel to this pixel, the probability of each of them being a shortest path, that's going to be a very complicated thing. And if you try to write the expectation, it's going to be the same. So this is one setting where things are very hard to write out explicitly. But on the other hand, it's very easy to sample from it. You just, add some noise and optimize. So now this means that, in a supervised setting, you can be in a situation where you have some features xi, you have some model output, so some theta that are taken from these features and that are the output of this parameterized model. And you want your prediction, you want your structured prediction to be this perturbed optimizer of theta w, right? So the idea is that ideally you would like this to be just the optimizer y star, but you add some smoothing here with this epsilon, with this perturbation technique. Now, if you have any loss L here, you can write the loss between the perturbed optimizer at theta and yi. And the idea now is you'd be looking for thetas such that y epsilon star of this theta is close to yi, at least according to this loss. Now you're trying to minimize this in W with gradient descent, Adam, your favorite optimizer. And when you're doing this, you need to compute gradients, and these gradients require to compute the Jacobian, so the sort of derivative, first order derivative of this soft optimizer as a function of the weights theta. And the nice thing, as I said, is that in order to compute this value and its derivative as well, you can do it with expectations. And so, at least to compute the value, the one thing that you have to do is you take some theta, the theta where you're trying to compute the value at. You create some, m IID copies of the noise. You solve, so often you can do this in parallel, right? You solve all of these instances of the problem with all of them a slightly different perturbation. And now you have an unbiased estimate of y epsilon star that's given by the average. So it's a Monte Carlo estimate, the average of all of these YL. And often, when you're trying to optimize these large-scale models, these neural networks, you're doing this with stochastic optimization. So the only thing that matters is to have, unbiased estimates of these gradients and of these optimizers. Now, so I mean, this is a part that's a bit technical. I mean, if you're interested in the math of this, this can be interesting, but it's not dramatically important. This means that also you have a one-to-one mapping between your whole set RT and your the convex hull of so this polytope of solutions. So this means if you can think of this means that if you want to change theta smoothly so that the perturbed output is close to some particular point of the polytope, this is actually possible. And now the differentiability. So all of these functions are smooth in the input. So it means that if you know the distribution of the noise, so often you'll use things like Gumbel or Gaussian, where you have these nice exponential of minus something for the distribution. So it needs to be positive and smooth. Then you will find that as I explained, it's easy to estimate y epsilon star just by using a sampler and y star, and it's actually also easy to estimate the Jacobian of y epsilon star, so the derivative with respect to theta, so this Jacobian matrix, again by just using these y star of theta plus epsilon z, and then the gradient of the log distribution as well. And so this means that both to compute the perturbed optimizer and its Jacobian, the only thing that you need to be able to do is to add some noise and compute in parallel a lot of these solutions. And in practice, this means also that your perturbed maximizer is never locally constant in theta. So you never have a gradient that's equal to 0. The other nice thing is that it's possible for given optimizers y star to implement automatically in your favorite library, so PyTorch, JAX, whatever, these automatic gradients. So you can have these sorts of y epsilon star blocks in your code that automatically compute their gradients. So now this means you have this sort of machine learning pipeline. So you start with features. This enters the model. You get these weights. Weights are go through an optimizer and are compared to y. And now what we've done is we've modified slightly this optimizer so that we have this perturbed optimizers, and these are the two things that we compare. So because of this small modification of the model, now it becomes end-to-end differentiable. So you have this whole package that's now entirely differentiable, as long as your loss is smooth as well. It's all fine. Now there's another kind of loss that we've looked at in this work that actually becomes easier to implement. It doesn't require to compute a Jacobian of the perturbed optimizer, and it's a loss that can directly act on theta. Right? So you'll still have to implement these perturbed optimizers, but now you get directly a gradient of the loss directly with respect to theta without having to say I'm doing a product of the gradient of the loss and the Jacobian of the perturbed optimizer. It's all together, and I'll explain how it goes. So the idea is that you have these stochastic gradients of the empirical loss. You have this particular loss that satisfies that the gradient with respect to theta is just the difference between y epsilon star and yi. Right, so it's a little bit technical of how you get to that. I can, if you're interested, I can get more into the details. But what's important is that this loss is minimized for theta at a value that makes sense, you can very easily simulate it by a doubly stochastic scheme, right? So you have some stochasticity because you're taking random xi, yi's to begin with, and also you're doing Monte Carlo estimates of these things. So you have doubly stochastic scheme, but all of it is unbiased. So, just like you are doing Monte Carlo estimates for the perturbed optimizer, what you have now is, you have this gradient of the loss directly with respect to theta. And now if you want to take the derivative of this with respect to the weights of the model, you just need to multiply this by the derivatives of the output with respect to the weights of the model. And this part is completely handled by whatever automatic differentiation library you have in Python. And so, the thing that makes us a little bit different is just this idea that here in this internal gradient of the loss with respect to theta, we have this doubly stochastic scheme. So we're also doing some Monte Carlo estimates. So now some experiments of this. So these are some experiments that we had in the initial paper. So the first one that we wanted to do was a classification. So even on a simple data set like CIFAR10 to understand what was going on, even with vanilla CNN. The idea is that in this case, the cross entropy loss, the softmax operators, they already exist. We know that we can simulate them with this perturbed setting, and we just wanted to show that you replicate the performance of the cross entropy baseline by using our loss, and so which is what we show here. The loss behaves similarly as the cross entropy baseline. And one thing that we found quite interesting is that you can see on the graph on the right, if you vary capital M a lot, or if you vary, these are the different graphs, or if you vary epsilon a lot also on the, the logarithmic scale on the right axis, you can see that, this operator is quite robust and stable to the choice of epsilon. And so this means that you don't need to be able to do a lot of cross-validation or hyperparameter picking. It's very stable to that. Of course, except if your epsilon goes to 0 completely, in which case, see that it's going to be not robust, or if your epsilon becomes way too large and eventually you're only getting noise. But if you're in this sort of very wide window between 10 to the -3 and 10 to the 3, then it's all the same.
Quentin, there is a question in the chat, so
Yep.
I will read it. What happens if we have two non-differentiable operations consequently? Do we take expectation of the noise also in a sequential manner or jointly?
That's an excellent question. I think both make sense. Both can be done. And you can kind of argue that this is the same with the loss. So as an example, there's people who consider losses that are only defined at the extreme points. And so this means that instead of taking a loss of the expectation, what they would do is they would take more a loss, an expectation of the loss at these random extreme points, and you can get slightly different results if you do that. My answer would be that, theoretically, both make sense. The composition of these can be considered, one discrete operator. And then it would kind of depend, you kind of have to check experimentally what works better. Both are well defined, taking approximations individually, taking approximations globally. Then it would kind of, depend on your use case. But it's absolutely true that, you can compose them individually in that way if you'd like.
Okay, thank you.
Thanks a lot for the question. So this is another case. So this is a learning to rank. So the idea, this is in this case, just a toy setting where we're taking batches of points. So we're getting 100 vectors that are projected along a secret direction and then ranked. And the idea is that you're trying to find this secret direction just by these ranks. So you have 4,000 instances of 100 vectors to rank. You add a bit of noise to this before you rank them, even in the data. And you see how a lot of these different approaches are kind of, robust to this introduction of noise. And you can see, so our method works really well, and it works really well in particular when you're considering this Fenchel-Young loss. If you're considering perturbation of the square loss, it doesn't work so well. If you're considering square loss without any perturbation, it works even worse. And the nice thing here is that, the Fenchel-Young loss also, it's convex in this secret direction in which you're projecting. So this means, you have more or less a convex linear model. You could have possibly a theoretical analysis of this, and you have theoretical guarantees. One of the experiments that seems a bit toy as well, but I really like, because it really looks like a magic trick at first. So again, we had this data set where you have some features like this, and you have some existing shortest paths that have been computed based on these costs, but you don't show the cost, right? So the idea is that there's some like unknown, at least to the computer, correspondence between features and costs. You can see, like forest that looks like this has a particular cost, lake has a cost that's higher, etc., etc. And you want your model to learn this just based on the data of features and shortest path. And initially, at least to me, it seemed like it was impossible. If you just show features and shortest path, how you can even learn from that, try to get costs that make sense, and that will be able, given new features, to predict the shortest path. And actually, we were able to do this. We were able to do this also much better than previous existing methods. And you can see here, after a short number of epochs, what we're getting is 90% shortest path accuracy. So this is, exactly an optimal path. And you can see also that, whenever you're wrong, you're actually not wrong a lot, because the cost ratio to optimal very quickly becomes, close to 1 up to a few percent. Okay, so now I'm going to present some follow-up work. There was an application of this framework to a particular problem in computational biology. It's called protein alignment. That was done with some of my colleagues were at Google at the time. It's been published recently. So first, what is protein alignment? I don't come at all actually from biology. And before I worked here with some of my colleagues who come from computational biology, I knew nothing about this. So the idea is that a protein is a molecule, and one way you can think about it is a list of amino acids. So amino acids are molecules that are kind of always the same. And one way you can think about them in a computer or in a data point of view is that it's a string of characters. There's a finite alphabet that you represent them with letters, and you have this very long word, and that's a protein sequence. And one of the things that you often like to do with these protein sequences is to learn character-wise embeddings, right? So one embedding per amino acid. And here, what we wanted to do this for was to use it to compute the cost of an alignment problem, right? So this means, you have these two sequences of proteins, right? They have some similarity. You can see, they finish by things that look similar. They both start with an A. They're not exactly the same, but they have some similarities. The question is, you have this A here that maybe, has to be mapped with this A, this T here that has to be mapped with this T. So you would like to have a problem that looks at these embeddings and says, oh, well, these embeddings should be close to each other because these two characters need to be mapped to each other because they actually, correspond to something. Maybe in the way these proteins have evolved, they're kind of the same. And so you can predict some alignment between these proteins. So I'll explain a bit more what's an alignment. And you can use this to have embeddings that make sense and that represent well what's going on in the protein. So alignment, what's this problem? So this problem is you have these two sequences, and you want to look at them and get this here, right? So what is this? Well, saying if we look at these two sequences here, if you just add the two empty spaces in the middle, you can see that a lot of these things are going to be the same exactly. Some of these are just going to be a change. Here, if you add 2 blank spots, you get another correspondence, etc. So then it just becomes, you have some fixed costs. So you have some costs of matching sequence letters that are the same, matching letters that are slightly different. You have, costs also for adding white spots, etc. And you have this algorithm called Smith-Waterman that's solved by a dynamic program that finds the way to match these by, inserting blank spots, matching those, or creating substitutions that gets you the best score as possible, at least, in terms of these substitution scores. So the substitution scores, for biologists, they are in a book. It's principled based on something. They're all integers, and it depends only on what the protein is, the length of the gap that you're creating, etc. So it's not per se data driven at all. So our approach was, is it possible to learn these substitution costs just from data, right? So we have data that kind of looks like this of, proteins that have been annotated by hand where, things look similar, or people have additional information that they play the same role in different animals, or that they have, different parts when you look at them in 3D that are matched to each other, etc. So we have some ground truth data like that. Just like, you can think of this as your like shortest path data that you had coming from this video game. And you'd like to create embeddings such that if you use these embeddings to produce scores and you push this through this Smith-Waterman algorithm, you get better alignments that match more the data than the existing classical algorithms. And so the way this is done is by introducing perturbations. So we take our framework of Smith-Waterman algorithm. So we have a sequence. It goes through a transformer model. This predicts contextual costs. This goes through the Smith-Waterman algorithm. Instead of having this hard algorithm, something that you can do is you can take all of these different possible solutions with perturbations and average them. This gives you like a soft or perturbed or differentiable alignment that can be used to learn from data, right? So you have something that looks a little bit more like this than the hard algorithm. That's what we use here. And so in the end, we have the system that we call DEDAL, so differentiable end-to-end alignment of proteins. It goes directly from sequences here. So at the training part, right, you go from sequences to embeddings, right? So this is a transformer model that transforms each character in the sequence into a vector. They all depend on each other, right? Because there's some cross character attention in here. Once these embeddings have been created, it goes through a bilinear system that creates these matrices of costs. So this is for substitution, extension, opening of a gap. This goes through our differentiable alignment. You get this soft alignment solution. And the alignment loss based on this Fenchel-Young perspective is used to compare this to data. And so this is what happens at training time. So you optimize directly the weights beta and phi so that your loss is minimized between your prediction and what you have in the training set. And at test time, you do the same thing, except all the weights here are frozen, and you use the non-differentiable, so just the usual Smith-Waterman algorithm to get a hard solution, and this is what your prediction is. Now, so just before I go to our results, one thing that this guarantees is that the predicted alignment that you're going to make is indeed a valid alignment, right? Just like if you use in shortest path, if you predict some underlying costs and then you use the shortest path algorithm on top of that, the prediction that you're going to make for the shortest path is going to be a valid path from point A to point B. Well, it's going to satisfy the constraints of a path adjacency matrix. Here, the same thing is true. So we have something that's biologically sensible as an output. Now, so we use this to compare to the best possible substitution matrix. So that's even better than what's done classically. Classically, there's a fixed substitution matrix that's used. Here we tried, what if you optimize even the parameters of that? So we're doing much better than this. This shows that leveraging contextual information is very useful. So in orange, we have our curve compared to the green one. We show particularly that this allows to capture similarity, weak similarity between sequences. So this is in a situation where there's very little similarity between the sequences, and it's allowed it manages to make much more accurate prediction than if you use the classical method. And this gap is particularly strong when you have a lot of similarity. Essentially, that's the idea. So as an example here, we get comparison between two animal proteins. So you have a protein that's in a gorilla and a protein that's in a type of duck, a mallard. I think it's a kidney protein. And here you can see, people have hand curated these by hand. So in green is, where things actually agree and are similar. And you can see that, if you try our method, so the dédale between this mallard protein and the gorilla protein, we get much more accurate results, a lot more green and a lot less red than if you use PFSM, which is the typical substitution matrix method for doing this. And you see also that the substitution matrices that we predict for this, the contextual one compared to the ones that are given by the usual algorithm, are a lot richer and capture a lot more, either things being in the same place in the protein or things that are far away that need to be put close to each other. These are from amino acids that are very strong and that are very useful to understand where things need to be connected in the protein, which is something that is grasped much less by the classical method. So really, I think this is again a strength of the transformer algorithm, of the transformer method, that we're able to connect to this alignment procedure. Okay, and finally, so we have this work. So this was with a very large team at Google Research and at Google Health, in collaboration with a biotech company that's called PacBio. And this was to improve an algorithm called deep consensus. So this is a model that tries to do a sequence correction with transformers with a loss that's gap aware. So we'll see what this means. So the idea is that PacBio they build these sequencing machines. There are big sequencing machines, big machines in a lab, wet lab, where you put biological material in, and weird things happen in the middle, and at the end there's a genetic sequence. So genes, DNA is a kind of protein, but with fewer characters, only 4 possible characters. That's outputted. So the genetic sequence is outputted based on this raw material. So I don't work on the wet lab part. The part that I worked on is, going from these from these biological data and getting, a lot of these small predicted parts. So the way this works is by, cutting genetic material and replicating it a lot. So you get a lot of these kind of short reads, and you're trying to, map all of them close to each other, and to create a sequence that makes sense out of all of this. So a lot of these parts classically were done by hand designed rules in the algorithm. Now that they are being replaced a lot more by these machine learning models. And one of the parts I worked on was this deep consensus algorithm that focuses on one part of the process. So the way this works is, you create a lot of these, reads. So, this is things that have been replicated in the biological sample that have been also read by the hardware. So there's possible mistake here. The idea is that you want to go from here to, through a transformer model to a prediction of this, small part of the sequence. And this is something that this team was already working on. One of the issues that they had was that, often when you have a lot of these possible subreads, if you look at the label, so the ground truth, that it looks like this. For some of these, the value of the prediction will be a bit hard to compute, because if you're doing this naively, if you're just looking character by character, if it's the correct value or not, then here you'd find that there's 10 wrong characters, and that this could be a problem. However, if you just figure out that you could shift things in the sequence a little bit, putting things together, adding some white spaces here and there, you would find that up to this rearrangement, the prediction error is only of 2. And the problem is that these sorts of rearrangements, they're not differentiable, right? So it's hard to have a loss that takes these things into account. And this is the part where they were stuck, and this is the part where we started talking with them and told them we were working on something similar, and we thought we had ideas and algorithms that maybe could work for this. And so this is what we worked on, deciding an aligned cross entropy loss, right? So character per character cross entropy loss that looks first at how it can first align these two sequences and then compare them. You can see that instead of assigning all of these as mistakes, if you properly align these, you can see that here you'd have possibly 2 mistakes, but here a lot more green, a lot more things that are valid. And so this was included in the model training for this particular project. We had to, differentiable alignment was used to generate much more accurate losses, and this was used used in the training and improved a lot the performance of the model. So the model that's been trained and that lives now in the hardware, in the PacBio sequencer that's called RevIO, has been trained in this manner. It's in the paper, it's all published. And the use of differentiable alignment was really crucial to generate these more accurate losses. Okay, so and these are some of the results that they got. So they were able to show if you use only cross entropy loss, even if you have a lot of extra features, the performance is much worse than alignment repaired by cross entropy loss, and that these other features are also interesting. So that's what I wanted to talk about today. So ideas coming from methodology, coming really from math, of trying to think of how we can modify these algorithms, how we can design these new procedures, these new losses in very challenging setting, and how we can apply them to very concrete settings in biology, in the sciences, where these very challenging situations occur. And thanks a lot for your attention. I'll be taking your questions if you have any.
Okay, thank you very much, Quentin. So it was extremely interesting. Hopefully colleagues are writing questions at the moment in the chat, so they can't speak, unfortunately. So I will start with probably a couple of questions from my side. So these applications to biology are very impressive, but in your initial paper, you have more like machine learning or like computer science applications, I would say. But relatively on more like a toy side, probably not really a toy side, but relatively simple problems. So since you have published that, did it find more like probably complex computer science applications? Someone applied it, someone extended it?
Yeah. So, I mean, first, this is something that's been applied, that's been picked up and applied by other people as well. So some people have applied it to differentiable rendering, in 3D rendering and graphics, and also differentiable physical simulations for robotics. Right. So I think the idea, I mean, again, I'm not an expert. I just saw the paper, but the idea is that if you have an object that's like this and you apply some force to pick it up, if you apply a small force, it's not going to move at all. You have to apply a force that's at least greater than the weight. And so this means that your gradients are going to be zero for a while if you don't do anything. So people have introduced noise or perturbation setting to improve the learning of simulation in robotics. Now, also recently, so I didn't mention this here, but recently one of the applications that we worked on with external colleagues as well, so Francis Beck at INRIA and one of his PhD students, Lawrence Stewart, is differentiable clustering. So the idea is that if you have some, clustering is a very discrete operation by nature, really, one of the most basic discrete CS problems. And you have, you're creating this big matrix for n elements of whether or not they're in the same cluster. The question is, how can you modify a little bit this clustering process so that it becomes differentiable and that you can learn from it also, right? So that if you have some data, you can learn. If you have some data, you can learn representations that agree with some with some of the clustering data that you have. So we showed that you can do things like some real data sets. You can do things like learn from very few labeled examples, even if it's missing classes. So if you're missing 3 classes, you can predict clustering on these data. And it's not, even if you have no clustering information about 3 of these classes that are completely unlabeled, you're not going to get 3 blobs. You're not going to get, 1 big blob. You're going to get 3 separate blobs. So somehow, the representations that you manage to learn that these things have to be in 3 different clusters, even though you're never giving it this sort of information. So these are the things that we're currently working on, and also kind of trying to see if it can be applied to more large scale settings, both in terms of models and data sets.
Okay, thank you. That's very interesting. For this last clustering project, is there any preprint available?
Yeah, I have a preprint. I think it's on archive. It's on my website.
Okay. We will find out.
Okay.
Okay, great. Yeah, we have a question in the chat again from Maxim, who asked another Maxim, who asked previous question on sequential discreteness. Now his question is, for standard differentiable models, a useful notion is narrow tangent kernel, which describes the gradient descent in function space. Can we extend the notion of NTK from deterministic gradient descent to perturbed one? For example, if NTK becomes some kind of a stochastic kernel, does the average dynamics of prediction depend only on the mean NTK, or statistical fluctuations become important?
Yeah,
what do you think?
No, I think that's a really good question. I had not thought of that. We had thought of looking at this for ensemble methods, right? So how you go from a network to kind of a distribution over networks by introducing perturbations. Not applying this to NTK, but I've never worked personally on NTK, but I wouldn't be surprised if this works. I would encourage you to pursue it if you're interested.
Okay, thanks, Quentin. Well, seems that no more questions so far. I have probably one small question. Can you go to the very last slide? I mean, before thank you one. Yeah, so I didn't fully get what is extra features here, because it seems like alignment loss just alone didn't provide that much, but then you add something called extra features and then you get a huge burst in performance. So can you give
what's
it?
a bit strange is that so these extra features, so there are, data augmentation features, etc. They're really only picked up by the alignment loss. They're not picked up by the cross entropy loss. So essentially, the long message of this is that the two together are necessary. These extra features, they are important. They are very useful, but they only manage to be useful when you're using also the alignment loss.
Is there any intuition to explain it, or it's more like empirical?
I have a weak intuition in terms of proteins. I'm not a computational biologist at heart. I'm guessing these extra features, maybe they have some sort of long range. They manage to capture long range interactions, so it's possible that this would not be picked up or seen by this cross entropy loss, because as long as you have, as soon as you have these sorts of gaps, it kind of, and the more apart you are in the sequence, the more likely it is that you'll have some gaps, etc., in the middle. So it's possible that these sorts of long range interactions are not accurately picked up by the cross entropy loss, and that this is what these extra features really manage to highlight. But this is extremely speculative. I wouldn't say this with extreme confidence, but it's one of the possible explanations.
Okay, that's very interesting. Thank you very much. So I don't see any more questions, so probably then it's time for us to conclude. So Quentin, thanks a lot. That was a very interesting, well, I'm overusing the word interesting, I should say exciting probably, which is true. And yeah, thanks a lot for coming. It was a pleasure to have you here, and yeah, hope to see you soon. So thank you.
Thank you very much.